You are welcome to the Physics Hub as we continue our study on dynamics. And in today's class, we are going to conclude our investigation on circular motion, and we'll be looking at the vertical circle. So by the end of this class, we expect you to be able to solve problems involving vertical circular motion, particularly calculating the tension keeping the object within the circular trajectory. Now, we have been talking about the horizontal circle, and we said in the horizontal circle, the key things are: number one, the tension in the string remains the same. The tension keeping the object in the circular path remains the same. And we said the weight and the tension are perpendicular to each other. They are at 90 degrees. Also, we said the gravitational potential energy of the object is always constant, as it is not changing its height from the ground. Now we want to drift and look at a vertical circle. A vertical circle is a circle in which an object, number one, has a top position. At one point in time, it's at the top. At another point, it's at the bottom. In other words, the gravitational potential energy of an object is constantly changing as the height with reference to the ground is changing. And because of that, we will see that the tension within the string is going to be changing. At the top of the circle, the weight of the object and the tension are in the same direction, helping each other, working together to provide for the centripetal force, which is going to keep the object in the circular trajectory. However, at the bottom, you see that the weight and the tension, they are opposite direction, meaning the tension is counteracting the weight, at the same time providing for the centripetal force, which keeps the object in a circular trajectory. So let's look into these positions one after the other. Let's analyze what really happens at the top and at the bottom, so that we come up with equations which are going to help us calculate the tension inside the string, since it's clear that the tension will be changing. Now, at the top of the string, at the circle, it is very, very important to note that the weight and the tension are moving in the same direction. The weight is always going downwards, seeking the center of the earth. The tension is always going towards the center of the earth, providing for the centripetal force, which is that all-important force. We said it maintains the object in a circular trajectory. By resolving these two vectors, weight is a force, a vector, tension is a force, a vector. Resolving them, since they are going in the same direction, we add them together. And since they are working together, they are providing for centripetal force. So we can safely say weight plus tension is equal to centripetal force. Now, from the previous studies, if you have not watched part 1 to part 3, watch circular motion part 1 to part 3. We said the centripetal force in a circular trajectory is given by the expression mv squared over r. So where there is centripetal force here, we can put this expression mv squared over r. And we also know that w is mg. So where there is w, we can safely put mg. Doing those substitutions, we have w for weight plus t for tension. It's f subscript c. Substitute mg for w and mv squared divided by r for centripetal force. We end up having this expression, and we want to find t. At A2, our most important part is finding the tension and comparing the tension at the top and at the bottom. We are going to have an expression which says the tension is mv squared divided by r minus mg. This is after making T the Sabatier formula. I'm going to call this equation number 1. Let's analyze what's happening at the bottom and come up with an expression for tension. It's clear that the weight and the tension are acting in the opposite direction. The weight, according to the system of reference, is going to the negative. The tension, according to the system of reference, is going to the positive. In this case, the weight and the tension is counteracting the weight. Hence, we can come up with an expression which says tension minus weight is equal to centripetal force. If two vectors are acting in opposite directions, one should be positive, then the other negative. Using the same expression for Fc and weight, we are going to have tension T minus weight W is F subscript C for tension, for centripetal force. Substitution, we know that W is mg, and we know that Fc is mv squared divided by r. Let's make T Sabatier formula. We will come up with the expression which says mv squared minus d over r plus mg is equals to T. Now this is going to be our equation number 2. Comparing these equations, the first equation, it has a minus. The second equation, it has a plus. Therefore, it is evident that the tension in vertical circular motion is not the same. It's changing. So how does it compare? Because of the positive on the second equation, it's very clear that the tension at the bottom is maximum, since the tension is counteracting the gravitational force, at the same time providing for the centripetal force. Now let's use an example to see if the numbers are going to agree with equation 1 and equation number 2. If we are to calculate the tension at the top and at the bottom, are we going to find the tension at the bottom to be greater than the tension at the top? Example number 1. A light string is used to swing a 2-kilogram ball in a vertical circle of radius 0.5 at a constant speed. Calculate the tension force in the string, number 1 at the top of the circle, number 2 at the bottom of the circle. I'll do the top, take a short break, you come back and present the answer for 2. Then I'll leave you with an exercise for more practice. Let's collect data. We are given the radius 0.5, we are given the speed 20 meters per second, we are given the mass 2 kilograms. What's the solution for A? We said at the top they are working together, and we came up with the equation which said tension is mv squared over r minus mg. That's the expression for the top. So let's take that expression and put substitution. Numbers for letters. Mass is 2, speed is 20, we square it, divided by radius 0.5. Minus at A level, A2, we are going to be using 9.81. This is for CIE students. 2 times 9.81. Punch your calculator, you should get 1580.4 newtons. Now let's take a short break and you work on B, then we compare the answers and make a conclusion. Welcome back. Let's go through part B, then you compare your findings with the ones which are coming to your screen. Now, for part B, we are at the bottom of the circle, and we said the tension is equal to mv squared over r plus mg. That's the expression we derived. Taking that expression and replacing numbers for letters, 2 for mass times 20 for speed, we square the speed, divided by 0.5 plus 2 by 9.81, you are supposed to get 1619.6 newtons. Now it is evident that 1580.4 is less than 1619.6 newtons. Therefore, we can, with sound mind, conclude that the tension at the bottom of the circle is greater than the tension at the top of the circle. I will leave you with these 3 questions for your practice. Enjoy your studies. Signing out is your senior coach, Chigo. See you in the next topic.